Hey everyone, welcome back to Chem Story. Today we're going to dive into a really important part of alcohol chemistry, substitution reactions. We'll talk about how alcohols behave in these reactions, why they're sometimes a bit tricky, and how chemists get around those challenges. We'll also go through some key mechanisms and real-life examples so you can see how it all fits together. All right, let's jump in. Let's start with something really important, the OH group in alcohols. When we talk about substitution reactions, the leaving group is a huge part of the story. In alkyl halides, it's pretty straightforward. The halide ions, like Cl- or Br-, are weak bases, which makes them great leaving groups. But alcohols? That's where things get tricky. The OH- ion is actually a strong base, and that means it's a poor leaving group. It just doesn't want to leave on its own. So even if a nucleophile comes in and tries to attack, the reaction usually doesn't go anywhere, unless we do something first. So how do we actually fix that problem? If we want substitution to happen, we need to turn the OH group into something that can actually leave. And luckily, there are a few good ways to do that. First, you can react the alcohol with the prussic acid. That protonates the OH group, and once it turns into water, it becomes a much better leaving group. Second, you can use a halogenation reagent like thionyl chloride or phosphorus tribromide to directly swap out the OH for a halogen atom. And third, you can convert the OH into an alkyl sulfonate, like tosylate or mesylate. These are excellent leaving groups and work great in substitution reactions. So these are the main strategies chemists use to get alcohols ready for substitution. Let's take a closer look at the first method, reacting an alcohol with a protic acid like HCl or HBr. When the alcohol reacts with HX, the OH group gets protonated and forms an oxonium ion. From here, the pathway depends on the type of alcohol. Primary alcohols go through SN2. The nucleophile attacks directly from the backside. But with secondary or tertiary alcohols, the oxonium ion first loses water to form a carbocation, leading to an SN1 mechanism. So in short, whether it's SN1 or SN2 comes down to the alcohol structure. Now let's break it down by alcohol type, because whether it's SN1 or SN2 really depends on the structure. Tertiary alcohols always go SN1. They form stable carbocations, so that path just makes sense. Secondary alcohols usually follow SN1 too, though conditions can make a difference. Primary alcohols, on the other hand, can't form stable carbocations, so they only react through SN2. And here's the reactivity trend. Tertiary reacts the fastest, then secondary, and primary is the slowest. But no matter which type you have, you can still turn it into an alkyl halide using HX, like HCl, HBr, or HI. All right, let's walk through a typical SN1 substitution, using tert-butanol and HBr as an example. First, the alcohol gets protonated, forming an oxonium ion. Then water leaves, and we get a tertiary carbocation, which is pretty stable thanks to the surrounding alkyl groups. Next, the bromide ion comes in and attacks the carbocation, and just like that, we get tert-butyl bromide as the product, with water as a byproduct. It's a classic SN1, 2 steps, a carbocation intermediate, and no backside attack. Now let's see how an SN2 reaction works, using a primary alcohol like 1-butanol. We're reacting it with HBr, just like before. First, the OH group gets protonated, turning it into water, a much better leaving group. Then the bromide ion comes in from the backside and kicks out the water, all in a single, concerted step. Since this is SN2, there's no carbocation. The whole thing happens in one smooth motion. You might be wondering, does the choice of acid matter? Absolutely. Stronger acids usually make the reaction faster, but faster doesn't always mean better. HI reacts the quickest, but the yield can drop due to side reactions. HBr and HCl are more reliable overall. And here's a helpful tip. If you're using HCl, adding zinc chloride helps a lot. It acts as a Lewis acid, activating the alcohol and making substitution smoother. So for the best balance of speed and yield, HBr or HCl with a catalyst is usually your best bet. Here's an example of how HCl with zinc chloride works, especially for primary alcohols. The lone pair on the alcohol coordinates with zinc chloride, which makes the OH group more electrophilic. That lets the chloride ion come in from the backside and do an SN2 attack. In the end, the OH gets replaced by a Cl, and you get an alkyl chloride as the product. So overall, zinc chloride activates the alcohol and makes the substitution much easier. Now let's look at another way to replace the OH group, using halogenation reagents. There are two main types. First, phosphorus halides like PCl3, PBr3, and Pi3. Second, thionyl chloride, or SOCl2. With PX3, the alcohol forms a phosphorus ester, and then a halide ion comes in and swaps out the OH group. With thionyl chloride, the alcohol forms a sulfonate-like intermediate, which then gets substituted to give you an alkyl chloride. So the idea is the same. Activate the alcohol, then substitute. But the reagents and mechanisms work a little differently. Let's take a closer look. Let's start with PX3 reagents. They work great with primary and secondary alcohols, and the reaction follows an SN2 mechanism, which means you get a backside attack and inversion of configuration. Since there's no carbocation ion, there's also no rearrangement. This method doesn't work well for tertiary alcohols, though they're just too bulky for SN2 to happen. And if you're doing iodination, Pi3 gives excellent yields, so it's a solid choice when making alkyl iodides. Let's take a closer look at how this mechanism works with phosphorus tribromide, or PBr3. First, the lone pair on the alcohol's oxygen attacks the phosphorus atom, and that pushes out one of the bromide ions. This gives us a charged intermediate, where the oxygen is now bonded to the phosphorus group. Next, the free bromide ion that got kicked out earlier comes back in and performs a backside attack on the carbon. That knocks off the entire OPBr2 group as the leaving group, and just like that, you end up with an alkyl bromide as your product. Next, let's look at another really useful reagent for alcohol substitution, thionyl chloride, or SOCl2. This method also works great for primary and secondary alcohols. But just like with phosphorus halides, tertiary alcohols don't react very well here either. Here's something interesting. The mechanism actually depends on the solvent you're using. If you run the reaction in pyridine, it follows an SN2 pathway, which means you'll see inversion of configuration. But if you carry it out in a non-nucleophilic solvent like ether, the mechanism switches to something called SNI, and that leads to retention of configuration instead. So depending on how you set things up, you can actually control the stereochemistry of the product. Let's walk through how the SOCl2 mechanism works in pyridine. First, the alcohol's lone pair attacks the sulfur in SOCl2, forming an intermediate where the OH is now linked to a sulfonyl group. Then pyridine removes a proton, helping stabilize the intermediate. Next, the chloride ion comes in, does a backside attack, and kicks out the leaving group, giving you an alkyl chloride. There's one more strategy you should definitely know, and that's converting alcohols into alkyl sulfonates. Here's how it works. You start with an alcohol and react it with something like R'-SO2Cl. That replaces the OH group with the sulfonate group. Now you've got a compound that's set up perfectly for nucleophilic substitution, just like an alkyl halide. And because sulfonate groups are excellent leaving groups, this method tends to work really well. Once this sulfonate is in place, you can bring in just about any nucleophile you want, and it'll swap in with no problem. So it's a two-step process, but it's super clean, and it gives you great control over reactivity. Now let's talk a little more about how we actually prepare alkyl sulfonates. There are two reagents that are commonly used for this: tosyl chloride, or TSCl, which gives you a tosyl group, and mesyl chloride, or MSCl, which gives you a mesyl group. Both of these reagents react with the alcohol and attach to the OH site, turning it into a really good leaving group. And here's something important to remember. There's no change in stereochemistry during this step. So whatever configuration your alcohol had, it stays exactly the same after the sulfonation. Let's briefly look at the structure of the two most common sulfanyl reagents. MSCl gives you a mesyl group, and TSCl gives you a tosyl group. Both work great for turning alcohols into excellent leaving groups, and which one you choose just depends on your reaction setup. Now let's take a closer look at how sulfonates are actually formed. It all starts when the alcohol attacks the sulfur atom on the sulfonyl chloride. That sets up a good leaving group, and then pyridine comes in to grab the proton, just like we saw earlier with the SOCl2 mechanism. By the end of this step, the OH group gets cleanly converted into a sulfonate. It's a simple, efficient transformation, and it sets things up perfectly for the next substitution step. Once the sulfonate group is in place, it acts as a great leaving group. So now, substitution can happen smoothly. A nucleophile, like ethoxide, comes in, performs a backside SN2 attack, and kicks out the sulfonate group. The result is a clean, stereospecific substitution with inversion of configuration. And that wraps up our lesson on substitution reactions of alcohols. We explored a variety of strategies, from using strong acids and Lewis acids, to halogenating agents like SOCl2 and PBr3, and even converting alcohols into sulfonates to improve leaving group ability. Each method has its strengths, and depending on your alcohol, you can choose the one that works best for your synthesis. Thanks so much for watching, and as always, I'll see you in the next Chem Story video.